Semiconductor MSQ multiple select question from NEST 2022 Shift 1, question 65. An unbiased silicon-based PN junction along with the net charge density profile is shown in the figure. The N and P sides are doped with phosphorus and boron atoms respectively, each of density 10 raised to 22 per meter cube. Taking Xn to be 3.3 into 10 raised to negative 7 meters and relative permittivity of silicon to be 11.7. Okay, taking Xn to be 3.3 into 10 raised to negative 7 meters and relative permittivity of silicon to be 11.7. Select the correct statement or statements. A. The electric field is in the negative x direction. Xp is 3.3 into 10 raised to negative 7 meters. The magnitude of the electric field at x equal to 0 is 4.9 into 10 raised to 6 volt per meter. And D, the magnitude of the electric field from xn to xp decays exponentially. Okay, now if the figure is not visible to you, let me show some things here. So this is our PN junction. Okay, this is the junction, PN junction. This side is P side, these negative charges, because the holes have diffused. Okay, and this is that positive. These are positive ions on the inside. Okay, positive ions on the inside because electrons have diffused to P side. Okay, this is this particular distance here is negative xp or coordinate. The center is the origin. Okay, this is negative xp, this is origin, this is positive xn. Okay, and then this is the net charge density shown here. So the charge density is uniform between xp and 0, and as usual, that being depletion region, this charge density is only due to the negatively charged ions there, and here it is the charge density in the n side of depletion region. Okay, so that W is the width of depletion region. Okay, W is the width of depletion region. Okay. Okay. Now let us go to A. They are saying option A, electric field is in the negative x direction. Now this is positive x. Okay, this is positive x. Now what is the direction of the electric field? What is the direction of the electric field? These are the positively charged ions. This is now electrostatic situation. Okay, positively charged ions on the inside, negatively charged ions on the p side. So what will be the direction of the field? The direction of the field will be like this. Now, will this field be along negative x? Yes. Considering the geometry, E bar will be negative EI cap. So will A be right? A will be right. Raise your hands if you have understood the argument. You already knew it. Electric field in unbiased condition of a diode after formation of the PN junction, immediately there will be barrier potential due to diffusion and drift equilibrium, and the field will be from N to P. Raise your hands if you have understood this. Okay. 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 Now let's come to B now. Let's come to B. Now in B they are saying XP. XP, that means the distance of this left end of the depletion region from the center PN junction, that is 3.3 into 10 raised to negative 7 meters. Now here is the thing. They have said that amounts of doping are same. Okay, so we can put it like this. Okay, we can put it like this. The charge concentration of P doping into the width of the depletion region in the P doping should be equal to the amount of doping in the N type into width of the depletion region type. Right? Well, that should be there to match the charge balance. Now because the density is same, Np is 10 raised to 22 and N is also 10 raised to 22. What does it give me? It gives me xp equal to xn. So width of the depletion region on the N side will essentially be the same, right? It will essentially be the same as that on the P side. So xn is 3.3, so xp will also be 3. So C is right. Sorry, B is right. Now let us come to option C. Okay, let us come to option C, where they ask us to determine the magnitude of the electric field at the center. Okay, they have asked us to determine the magnitude of the field at the center. So to do that, to get that, let us go to the figure again. Okay, fine. So we would like to find the electric field here. Okay, now a few things I would like you to remember or recall from our discussions on electrostatics. Okay, so if we have a thin sheet, okay, suppose if we have a thin sheet, okay, if we have a thin sheet of uniform surface charge density, okay, if we have a thin sheet of uniform surface charge density sigma, then the field due to that will be given by sigma by epsilon, sigma by 2 epsilon. Okay, this is the standard result from our first chapter. If you haven't, if you are unable to recall it, let me show that to you. Field due to uniformly charged infinite plane sheet. Okay, infinite plane sheet, and here is the field. We can use it as an approximation here. E bar is equal to sigma by 2 epsilon naught n cap. Okay, this is the formula that I'm talking about. Okay. Now I have deliberately not used epsilon naught there because it's not vacuum anymore. It's our silicon. Okay, doped silicon. This is equation 1.33, 1.33. So I'm putting it here as your reference. Okay. Now look here. I'm going to make a statement. I'll say field at x equal to 0 is due to superposition of electric fields by thin slices. Okay, thin slices cut perpendicular to W, or let me say perpendicular to x-axis. So what I'm asking you to visualize is, I'm asking you to consider, okay, I'm asking you to consider the depletion region. Okay, I'm asking you to consider the depletion region like a bread loaf, like this. Okay, and this is that x equal to 0 line. Okay, x equal to 0 line, and what I'm saying is, let us cut this depletion region into bread pieces. Okay, I'm going to show two of them here. Okay, one here, and then let me show you the other one here, like this. Now each one of these fields will contribute equally because the charge configuration or surface charge density is same. Raise your hands if you understood this. Look here, now if this is that positively charged thing, the contribution here due to this will be along this, and the contribution due to this negatively charged will also be towards it. Okay, so effectively everything will get added in the same direction. We already determined the direction. Okay, please note that this is a vector equation. this is a vector equation and this is a scalar equation. Having already determined the direction, we are now only interested in determining the magnitude. Raise your hands if you have understood this. Yes, okay, okay. Now, because the surface charge density is uniform, okay, not the surface charge density, the volume charge density is uniform, we can argue like this. Okay, suppose the width is dx. Okay, suppose we go for the width. Okay, let's say we take the section and suppose this width is dx. Okay, so can we calculate sigma? Yes, we can calculate sigma. How to calculate sigma? To calculate sigma, we must first take into consideration the total volume charge density. Okay, what is the volume charge density? Density is 10 raised to 22. Okay, and each will contribute one hole or one electron. Okay, so that is n. But this is only the number. If we multiply it by the charge, then we will get the total charge, Ne. Okay, but this is per unit volume. We want it per unit area, so this must be multiplied by dx. Raise your hand if you understood this. We must multiply this by dx. Have you really understood this? Or no? Look, this is per unit volume. This is in coulombs, charge on electron, and what is dx? Dx is in meters. So effectively it will be in coulomb per meter square. Have you understood this or you haven't? Rajat understood? Okay, great. So what will be the elementary field or field contribution? Because the field is independent of the distance, we can say that d is equal to Ne dx upon 2 epsilon r. What is epsilon r? Epsilon r is the relative permittivity. Got it? Epsilon r is the relative permittivity. Okay. Now, therefore, E net. Now look here. The whole of the depletion region, which is to the right of x equal to 0, this part, this is going to contribute positively, and this is also going to contribute positively in the sense that the effects of the electric field due to that and this, they are not going to cancel each other, they will get added actually. So I can say effectively E net is equal to, magnitude wise, 2 times Ne upon 2 epsilon r dx, and dx is going from 0 to xn or xp, whatever it is. But now because we have taken xn to be positive, let's go. Okay. Now what is xn? Now let's invoke the numbers now. Okay, let's put the numbers. Xn is 3.3 into 10 raised to negative 7. Okay, xn is let's come to the integration part later. Okay, this is 0. First of all, we'll start with n. What is n? 10 raised to 22. Given. 10 raised to 22 is given. Take it, 10 raised to 22 is given. Okay. What is E? E is 1.6 into 10 raised to negative 19 charge on electron. 2. What is epsilon? Does anyone remember what is the value of epsilon or epsilon naught? Sorry, epsilon naught.
8.85 into 10 to the power minus 12.
Yes, 8.85 to 10 raised to negative. Very good. And what is the relative permittivity of silicon? Relative permittivity of silicon is 11.7. Given 11.7. Okay. And xn is how much? How much is xn? 3.3 into 10 raised to negative 7. Okay, so basically once we evaluate this, we will get the value of the electric field at the center. Let's do that. First of all, as we typically do, let's only go for the digits. So 1.6 into 3.3 upon 8.85 into 11.7. So that is 0.05099. And now let's go to the powers of 10. Negative 90 minus 7 plus 12. Oh, okay, plus 22. Sorry, plus 22. Eight. Okay, 8. So it is basically 0.05 into 10 raised to 8 or 5 into 10 raised to 6 Newton per coulomb or volt per meter. And that's pretty close actually, 419. So option C is right. Okay, C is right. So A is right, B is right, C is right. Now let's go to D. Okay, let's go to D. The magnitude of the electric field from xn to xp decays exponentially. Okay, now look here. Forget about the word exponential. Let's go to the word decay. Okay, let's see why it's not the right way to put the situation. Let's again go to this. Okay, let's again go to this. Now look, this is your xn and this is xp. Okay, if I ask you to tell me the field at xn, that will definitely be 0, right? Because there are equal positive charges to the left and also equal negative charges, right? And what is E of negative xp or E at xp? That is also 0. Okay, that is also 0. And what is happening at E? What is happening to the electric field at 0? Well, at the PN junction, that is not equal to 0. No matter what the value is, that is not equal to 0. So it is definitely, so if it decreases from, if we consider, if we go by the magnitude, if we go by the, well, magnitude and direction, then look here, here the field is 0 at xn, at xp also the field is 0, but here the field is not 0 at the center. I'm considering it negative because of the sense of the positive x. Okay, so let's take it negative here, which means no matter in which way, whether linearly, exponentially, it decreases here, it must increase here, which means as E decreases between xn and 0, it must increase between 0 and xp. It must increase between 0 and xp, which basically means that a decrease must be accompanied by an increase, and that contradicts with the word decay. Decay usually means always reduction, like population decay. The radioactive sample decays, which means the number of radioactive nuclei reduces, but it never increases. But here the field is increasing, or we can say the other way, if it is decreasing from xn to origin, then it has to increase again to 0 from origin to xp. So E is option D, right? Option D is not right. It although doesn't decay exponentially, it decays, it changes linearly. So the graph is like V here, like the mod function. I will show the graph to you. Okay, the graph is actually like a mod function. You can derive it, but that's not necessary to be known to solve this particular problem. Okay, so option D is not right. A is right, B is right, C is also right, but D is not. Okay, fine. Now, here is the picture that I wanted you to note. Okay, in our case, the doping concentrations were equal, but if they are not equal, then the width of the depletion region from in the p side and the inside will be different, because the product that we took as a constant np xp nx nn xn, that product is always constant. So depending on the nn and np levels, xn and xp will change. Okay, so this is the charge density that we had seen. Okay, this is the charge density. This is the current flow that we usually draw in unbiased condition, electron diffusion drift, hole diffusion drift. Okay, and this is the electric field. Okay, this is the electric field. Because the width was not is not uniform here of the depletion region in p and n sides, the slopes are different. Okay, but otherwise the slopes are same in the sense that uh, this angle and this angle are same, but here they are not same. Okay, this is electric field, and because electric field is changing linearly, the potential, which is the integral of the field, will vary quadratically. So this is parabolic. Okay, this is parabolic variation.